Philosophers and scientists have long been fascinated by the nature of reality. One of the most intriguing concerns is whether our reality exists or is merely a mental illusion. The advancement of quantum physics has brought new insights into this subject, allowing us to investigate whether our reality exists or is simply an illusion. Quantum physics studies the behavior of matter and energy at the microscopic scales, where classical physics no longer makes sense. It also looks at how matter and energy behave at the atomic and subatomic levels. Quantum physics concepts differ vastly from classical mechanics principles, which describe the behavior of matter and energy at macroscopic scales. The study of quantum mechanics has revealed several unusual phenomena that are not easily explicable using classical physics. The concept of wave-particle duality, which posits that all particles can show wave-like and particle-like behavior, is at the heart of quantum mechanics. This means particles like electrons and photons can act like waves and display interference patterns. This behavior is in striking contrast to classical mechanics, in which particles are always treated as particles and waves as waves. Superposition is another fundamental concept in quantum mechanics. Particles, according to the principle of superposition, can exist in multiple states at the same time. For example, an electron can exist in several different energy states all at once, and the electron only collapses into a single state when an observation is made. One of the most intriguing aspects of quantum mechanics is the wave function collapse, also known as the measurement problem. This concept contradicts our classical notions of cause and effect by implying that a particle's behavior is not determined until it has gotten observed. Some physicists believe that reality does not exist because of the measurement problem. According to this viewpoint, reality exists only when we observe it. This is known as the observer effect, which argues that our consciousness shapes our reality. This view has been supported by several experiments, including the double-slit experiment, which demonstrated that observation can change the behavior of particles. A classic example of the observer effect is the double-slit experiment. In this experiment, a beam of particles, such as electrons, is fired at a screen containing two slits. When particles flow through the slits, they form an interference pattern on a detector screen behind the slits. However, when the particles are examined as they pass through the slits, the interference pattern disappears and is replaced by a single particle pattern. This experiment shows that simply observing particles can affect their behavior, implying that our reality is not fixed, but rather formed by our consciousness. Entanglement is another fundamental concept in quantum physics. Entanglement occurs when two particles become entangled in such a way that the state of one particle is reliant on the state of the other particle, even if they are separated by a significant distance. The classic thought experiment of Schrödinger's cat is frequently used to clarify this concept. In this thought experiment, a cat gets placed in a sealed box with a vial of poison. The vial is wired to a quantum mechanical event, such as radioactive atom decay. If the atom decays, the vial will break and the poison will be released, killing the cat. The cat, however, is in a state of superposition until the box is open, existing in both the alive and dead states simultaneously. The thought experiment illustrates the notion that reality does not exist unless it is observed. The cat is neither living nor dead until the box is opened and examined. It exists in a superposition state. This experiment has prompted the question of whether reality exists at all until it is viewed. The Copenhagen interpretation of quantum mechanics is one interpretation of quantum mechanics that supports the idea that reality is not objective. The wave function collapse, named after the city where it was first proposed, is a clear physical event that occurs when a particle is observed, according to this interpretation. This event implies that reality is not predetermined and that observation is critical in shaping it. This interpretation has led some to believe that our reality is only a product of our imaginations and that there is no reality without observation. The experiment on the wave function collapse that I spoke about earlier suggests that the act of observation changes the behavior of the electrons, which supports the idea that reality gets shaped by our observation. There are also many other interpretations of quantum mechanics besides the Copenhagen experiment. Another interpretation is the many worlds interpretation, which posits that any scenario that could result in an event does take place in a parallel reality. According to this interpretation, the act of observation chooses the cosmos we experience rather than creating reality. Even more illogically than the Copenhagen interpretation, the many worlds interpretation is supported by some quantum physics experiments. The delayed choice quantum eraser experiment is one of these experiments, and John Wheeler first suggested it in the 1980s. The screen in this experiment has two slits, and a beam of photons is shot at it. A sensor that can identify which slit photons flow through is located behind the screen, but is not activated until the photons have already done so. An interference pattern appears on the screen of the sensor right after the sensor is turned on, because it erases the information about which slit the photons pass through. The photons, on the other hand, behave like particles when the sensor is off and do not produce an interference pattern. This experiment suggests that while observation can affect an event's outcome, the reality is not always the result of observation. Instead, the many worlds interpretation claims that each possible outcome of the experiment takes place in a parallel dimension, and that the option of which universe we experience depends on the act of observation. Even though these experiments lead to the conclusion that our reality is not genuinely real, they still face strong criticism. According to some physicists, these experiments only show that we have an incomplete grasp of reality, rather than that our existence is not real. They suggest that there might be additional elements at work that we are not yet aware of, and that these other factors could account for the peculiar behavior of particles. According to some scientists, the idea of wave-particle duality, entanglement, and superposition does not necessarily indicate that our reality is unreal. They contend that these notions reflect how particles behave at the quantum level, and that at the macroscopic level, particles behave more in line with classical mechanics. In light of this, even though quantum mechanics may challenge our understanding of reality, it does not necessarily mean that our reality is not real. Despite these objections, the notion that our reality is not real has gained ground recently, especially with the emergence of interpretations like the simulation hypothesis. The simulation hypothesis posits that an advanced civilization or computer program built a simulation of our reality. Although this theory has been discussed in science fiction for years, it has recently gained traction due to the backing it has received from physicists like Elon Musk and Neil deGrasse Tyson. The simulation hypothesis is based on the notion that it is increasingly possible to imitate complex systems, including our reality, as technology develops. According to the theory's proponents, if it is conceivable to simulate our reality, then a more sophisticated civilization or computer program has probably already done so. This would imply that reality as we know it is merely a simulation of an advanced civilization. Even if the simulation idea is appealing, it's crucial to remember that there isn't any concrete data to back it up. It is also unknown what effect this would have on our lives, even if it were true. This notion has sparked a series of questions about whether our experiences and feelings are authentic if our reality is a simulation. Or does it just mean that our reality is formed by a different means than we previously thought? Although these are tough questions to answer, they highlight the intricacy of the thought that our reality is not genuinely real. While these interpretations of quantum physics may seem far-fetched, they have been supported by several experiments over the years. However, there are still many questions that remain unanswered, and many physicists are still searching for a more complete understanding of the nature of reality. The study of quantum computing is one possible way to delve into the nature of reality. Calculations that are not conceivable with classical computers are made possible by quantum computers, which operate on the principles of quantum physics. In addition to potentially revolutionizing industries like machine learning and cryptography, this technology may also shed light on the nature of reality. For instance, some researchers are looking into the possibilities of simulating quantum-level particle behavior using quantum computers. This might offer new perspectives on the concepts of superposition and entanglement and aid in understanding the true nature of reality. Another area of research is the study of quantum mechanics in the context of the theory of relativity. The integration of quantum mechanics and relativity into a single, comprehensive theory of physics has not yet been achieved, although both have received remarkable success in their respective fields. Some scientists think that studying quantum physics in the context of relativity may offer new perspectives on the nature of reality and ultimately result in a more thorough comprehension of the universe. So can we say our reality does exist? The answer to this question is unclear, as it depends on how we define existence. If existence is viewed as a constant, objective reality that exists independently of our observations, the probable answer would be no. According to the fundamentals of quantum mechanics, our reality is not static. Rather, it is a product of consciousness. However, if we see existence as a subjective reality shaped by our views and experiences, the answer is probably positive. Although the concepts of quantum mechanics present challenges to our conception of reality, this does not necessarily imply that reality as we know it is not real. And that's a wrap on today's video. Do you think our reality is real? Let us know in the comments section. We hope you enjoyed this video and learned something new today. And as always, keep exploring.